Okay, so we want to do an example problem where on one side of this we have someone climbing up a ladder, and of course this is the sort of thing you should sketch out the problem. Right. And the ladder itself has some weight to it, and then the firefighter here, it's spraying water in a window, has some weight. Right. So we have our different measurements here, and we want to figure out what the forces are that's present that's making everything work. Right. So the wall's frictionless here. There's no friction here, but here there is friction. So, we've kind of drawn this out a little simpler. And what we want to do is simplify it even further. We're going to draw something that looks like a free body diagram, but it's going to be kind of extended. We're going to put the ladder in. I want to say one end is 0 and one end is 8 meters away for that length. So we'll mark this end as some point, and this end is some other point. So right in the middle is the weight of the ladder, and that is always going to be straight down. Right. Then somewhere up here, there's going to be a weight for the firefighter. That's going to be some distance up. And so if we're measuring from this end, if this is X is 0, this is X is 4 meters. And then in the Texas problem, this is X is 6.3 meters. Right? And then the other end is X is 8 meters. So there's some other forces involved here. Right? On the ground, this thing's going to try to slide to the right. So there has to be some force here that is a frictional force of the ladder on the ground. And there has to be a normal force because there's a surface and there's a friction force. Right. So that's going to be those points there. But there also has to be something on the wall. Now there's no friction up here, but there is a normal force associated with the wall. So there's the wall, and then we'll put in that this is the ground, and this is the ground. Right. So that's our goal, is to come up with this diagram to figure out what's going on in the problem. Right. So if you look through the notes, this is what I've drawn out eventually in the notes. And then we got to solve and try to figure out what all the torques and what all the forces are. And so what I'm going to do is suggest that we have a bunch of stuff we don't know. We know the weights, and we don't know any of these normal forces or friction forces. So we can come up with some expressions, right? We can say that the sum of the forces in the y direction, well, what's in the y direction? Well, there's this normal force based on the ground holding the ladder up, and there's going to be a weight force from the ladder, and that's downwards, and there's going to be a weight force from the firefighter on the ladder. So we're going to take up as plus y and across as plus x, and we're also going to say that rotation in the counterclockwise direction is positive theta. That's going to be kind of important when we start talking about torque. So that's the sum of our forces, and that should be 0 in the y direction. Now in the x direction, sum of the forces in the x direction, well, there's this normal force that the wall puts in, and it's actually negative. It's in the negative direction. And there's a frictional force the ground puts in. and that's going to be 0. And then finally, we can deal with the actual torque. So the sum of the torque, and what I'm going to do is make some notation up. But we have to put in all of the different torques that are existing. So, well, there's going to be torques from these two things. Plus, now these are all vectors, so I'm just going to add all the vectors up. The torque of the ladder plus the torque of the firefighter plus the torque of the wall pushing back. And all of those equal 0. But when we look at this, there's a bunch of unknowns. We've got 3 equations, and we've got effectively 3 unknowns. But we don't have enough ways of linking the stuff together. We need to kind of cancel some stuff out. And so what we're going to do is, this thing's not rotating. Right? The ladder is nice and stationary here. So any point can be the point that it rotates around. So I'm going to put it here nice, bright, and pink. This point at the ground, that's going to be R equals 0. So that means we can go in and say what these torques are. And this is R equals 0 times this ground force plus R equals 0 times this frictional force plus, now R is 4 meters times our weight force. And the weight for the ladder is 355 newtons. And it is, in this case, it's downwards, so it's negative. Plus, and then we'll have R is 6.3 meters, and we'll have our weight force here is 875 newtons, but it's downwards, it's negative. And then we'll have our R is 8 meters times the normal force for the wall, and all that equals 0. And now we can look at this. Anywhere where R equals 0 is, the whole term goes to 0. So those things go away. And now we just have one unknown. We can solve for the force the wall puts on the object. And what I'm realizing here is that there's a lot of math that hasn't been seen in here. And we should put in some other things. There's some angles in here that we need to put in. I need to be very careful of this. So this ladder makes this 50-degree angle. So in here, this is 40. And so this is 180 minus 40 is 140 degrees. But we're counting for that here in this minus sign. So there'll be sine of 40 degrees here. There'll be sine of 40 degrees here. Here, this angle is 50 degrees. All right, because this is 2 parallel lines. The ground and this horizontal force from the wall are horizontal. So 2 parallel lines and a line going through it, these angles are equal. And then this is going to be 130 degrees. Either way, we should end up with sine of 50 degrees. So that's where the stuff is going to come from in the notes. But I'm realizing that I'm showing you this stuff in the notes. It doesn't necessarily make, you sort of run out of space. So the gist of it is This lets you get this one thing that you need, the normal force that the wall provides. And then you can use that, you can plug in and get the frictional force that the ground provides. And you can get the normal force the ground provides up here. That you don't need rotation for. We already know what that is. So we just need to get this frictional force. So if we go and we plug and chug all through this, we're going to have 4 times 355 times 40 sine. This first term is minus 913. And then we're going to add 6.3 times 875 times 40 sine. So together these things are 4,500. And now we're going to divide by 8, and we're going to divide by 50 sine. And so what we get is that this normal force that the wall provides is minus 727 newtons. That just means it's to the left. Well, that means the frictional force that the ground provides is plus 727 newtons, because it's to the right. That's a lot, right? There's a lot of maneuvering around that problem. And you're going to want to see more examples of it, right? We're going to have to go through some more material here, so bear with me on it. How do I stop this?